Welcome all. We are going to continue with the chemical properties of S block elements. Let's check how chemical properties will differ from the physical properties of the S block elements. Now, basically, we need to talk about the diagonal relationship that though they have group 1 elements or group 2 elements have same electronic configurations throughout moving from top to bottom or top to bottom down the group, yet they differ chemically, though they have to be similar, but they differ chemically as the lithium or group 1 first element do not behave similar to rest of the group 1 element, but it behave like the second element of the group 2. Whereas first element of group 2, that is beryllium, do not behave as rest of the element present in the group, but it behaves like the second element of group 13 and so on. You can check in the um, picture given over here. So what is diagonal relationship? Diagonal relationship shows similarities between the pairs of elements, different groups and periods of the periodic table. Hence, this few reasons noted for the anomalous behavior of lithium. Now, what are the anomalous behavior of lithium with respect to other alkali metals? First, that is the melting and boiling point of lithium are higher than other alkali element, higher than other alkali metals. The hardness of lithium is higher than other metals, and lithium nitrate decomposes to form an oxide. I repeat, lithium nitrate decomposes to form an oxide. Whereas other metals, means other alkali metals, on heating give nitrites. Hence, the reason for these anomalous behavior of lithium are its extremely small size, it has a greater polarizing power, least electropositive character because it undergoes the covalency in nature, and non-availability of d orbital. So the whatever anomalous behavior means the behavior other than the alkali metals, it shows it is due to the four reasons, that is extremely small size, it has greater polarizing power, it is having least electropositive character and non-availability of d orbitals. Next, when S block elements are reacting with oxygen, hence what we need to think is S block elements are strong reducing agent. As metals, we know they are able to donate or lose its electron, hence they are acting as in reducing agents. The reducing powers increases down in both the groups. That means common for group 1 as well as group 2. As the atomic size increases, it becomes easier to remove the outermost electron of an element. S block elements react readily with oxygen. Except beryllium and magnesium, they have to store under liquid paraffin to prevent contact with the atmosphere. For example, we have already learned in grade 10th as well, that is lithium, sodium and potassiums are supposed to be kept under kerosene so that they do not come with direct contact with the atmosphere. Otherwise, they are highly reactive with the oxygen and they burn and produces pop sound. Hence, these are the reactions with the oxygen. Normal, they form oxides. Otherwise, they form peroxides or superoxides. So, which elements can form peroxides? Sodium and barium can form peroxides, whereas potassium, rubidium, and cesium can form superoxides. But lithium, it can only form normal oxides. It cannot form peroxides or superoxides. Next comes reactions with water. When we are talking about reactions with water, metals, M solid metals, it first of all will release its electron. That is when we are talking about the group 1 element. Then water releases with it. It will form the oxides first. Metal will form oxides and then it will convert into the metal hydroxides. So here we have the energetic versus the kinetic factor. You can see that. Next, when we are talking about reactions with hydrogen, so metals reacting with hydrogen forms metal hydrides. Now, when it forms metal hydrides, at that moment, the valency of hydrogen is -1. Except beryllium reacts directly with hydrogen. The reactivity increases down the group. Only beryllium hydrides and magnesium hydrides are covalent, and rest all hydrides of group 1 and group 2 elements are ionic in nature. When we are talking about the group S block elements reacting with chlorine, it produces the chlorides. Now, all group 1 elements, that means all group 1 chlorides are ionic. Exceptional for the group 2 is beryllium chloride is covalent. This we have already learned in chapter 4, chemical bonding as well. That is, it do have a linear shape with comparatively low melting points. The lower members in group 2 form essentially ionic chlorides with magnesium having intermediate properties. Magnesium chlorides can act as ionic as well as covalent. Although lithium has highly negative energy, that is E0 means its electromotive force, it only reacts slowly with water. This illustrates the importance of role of kinetic factors in determining the rate of a chemical reaction. Lithium has a higher melting point, which increases the activation energy required for dissolution in aqueous solution. It does not melt during the reaction as sodium and potassium do, and thus it has a smaller area of contact with water. And this is the reason why lithium forms covalent bonds in between. Till now, we have seen variation in properties of the elements. Now we are going to see the variation in properties of the compounds. So what are topic we are going to see? We are going to see the reactions of oxides and hydroxides, reactions of chlorides, reaction of hydrides, thermal stability of carbonates and hydroxides, and relative solubility of sulfate and hydroxide. So reactions of oxides and hydroxides, when we are talking about, all group 1 oxides reacts with water to form the hydroxides. This we have discussed when we were saying that the group 1 and group 2 oxides are basic in nature. That means oxides reacting with water, that means dissolves in water, it forms the hydroxides. Here you can see when oxide dissolves in water, we obtain hydroxides. Whereas when peroxide dissolves in water, we again obtain hydroxides. Even superoxides dissolving in water, we obtain hydroxides, peroxide, and oxygen gas. All group 1 oxides or hydroxides are basic in nature and the basicity increases down the group. Next, when we are talking about the reactions of oxides and hydroxides, group 2 oxides or hydroxides are generally less basic than the group 1. Beryllium oxides or hydroxide is amphoteric in nature. Amphoteric in nature means at times it can act as acidic, at times it can act as basic. Next, when we are talking about reactions of chlorides, we already talked that when group 1 metal forms chlorides, these all chlorides are ionic and readily soluble in water. Hence, no hydrolysis occurs over here. But group 2 chlorides show some degree of covalent character. I repeat, group 2 chloride shows some degree of covalent character. Beryllium chloride is covalent and hydrolysis to form beryllium hydroxide and HCl. Magnesium chloride is intermediate. It dissolves and hydrolysis slightly. Other group 2 chlorides just dissolve without hydrolysis as similar to group 1 chlorides. Next, reactions of hydrides. We are talking about the variations in the properties of the compounds. So hydrides readily react with water to give metal hydroxide. Here as well, hydrides readily react with water to give metal hydroxides and hydrogen due to the strong basic property of the hydride ion. Hence, hydrides plus water gives hydrogen gas plus hydroxide. Hydride ions are also good reducing agent. They can be used to prepare complex hydrides such as lithium aluminum hydride, sodium boron hydride, which are used to reduce carbonyl group in organic chemistry. When we are talking about thermal stability refers to decomposition of the compound on heating. Increased thermal stability means a higher temperature needed to decompose the compound. Thermal stability of carbonates, when we are talking about lithium carbonate decomposed, gets decomposed at 700 degrees Celsius into lithium oxide and carbon dioxide. All other group 1 carbonates are stable at 800 degrees Celsius. Next, we have group 2 carbonates, that is beryllium carbonate at 100 degrees Celsius. Now, as you can see, as we are moving down the group, the temperature increases. The temperature of the carbonates to get decomposed is increasing. Thermal stability of hydroxides. All group 1 hydroxides are stable except the lithium hydroxide at Bunsen temperature. Whereas when we are talking about the thermal stability of hydroxides of group 2, you can see again the enthalpy, that is change in enthalpy, is increasing. Right, as you can see, the more amount of energy is absorbed, and that is the reason why it is positive. A general one, carbonates and hydroxides of group 1 metal are as a whole more stable than those of group 2. Thermal stability increases down the group. You can check, right? We have seen that it requires more amount of temperature. Lithium often follow the pattern of group 2 rather than group 1. This is, as we have discussed, of the diagonal relationship. Now, thermal stability is related due to the charge of the ions, size of the ions. Compounds are more stable if the charge increases and size decreases. For compounds with large polarizable anions, thermal stability is affected by the polarizing power of the cations. Thermal stability is defined as the ability of a fluid to resist breaking down under heat stress. I repeat, thermal stability is defined as the ability of a fluid to resist breaking down under heat stress. As such, the maximum use temperature is the suggested maximum temperature to which the fluid can be heated before the fluid begins to break down or degrade at an appreciable rate. Hence, you can see if it requires more temperature, that means those compounds are more thermally stable. Hence, you can see the polarizing power increase in stability. Right here, we do talk about the polarizing power of the thermal stability. So, thermal stability depends on the polarizing power of the cation, which in turn is determined by the charge density. This is the polarizing power of a cation, whereas this is determined as the charge density. The larger the charge, the smaller the radius and greater the charge density. Cations that strongly polarize the anion are more easily decomposed than those with less polarizing cations. Therefore, less energy is needed to break up the molecule as a whole. Thus, the greater the polarizing power, lower the thermal stability. Right here, greater the polarizing power, lower the thermal stability. That means polarizing power and thermal stability are inversely proportional to each other. Here, decreasing polarizing power down the group, increasing thermal stability down the group. Here you can see how the thermal stability is acting on the carbonates and hydroxides. Hence, in general, we can say that is for a particular set of group 1 and group 2 compounds, the thermal stability the thermal stability increases down the group as the ionic radius of cation increases and its polarizing power decreases. Group 1 compounds tends to be more thermally stable Then group 2 compounds, because the cation has a smaller charge and a larger ionic radius, and so a lower polarizing power, particularly when adjacent metals on the same period are compared. Hence, the order of increasing thermal stability is beryllium carbonate less than magnesium carbonate less than calcium carbonate, which is less than potassium carbonate. Here, when we are talking about the solubility of group 2 hydroxides, you can see the solubility of hydroxides increases down the group per mole. Even solubility of group 2 sulfates, you can see the solubility of sulfates increases up the group. That means as we go down the group, the solubility of sulfate decreases. Right. We all know group 2 metal oxides basicity and hydroxide solubility in water increases as you go down the column. Beryllium oxides and beryllium hydroxides amphoteric, this we have already talked about. Now, the solubility of group 2 sulfate, why decreases down the group? The reason is the hydration enthalpy decreases. Repeat, the hydration enthalpy decreases the same way as it does in the case of group 2 cations bonded to hydroxide ions. Since the hydration enthalpy decreases faster than the lattice enthalpy in case of group 2 sulfates, the solubility of group 2 sulfate decreases while progressing down the group. Here you can see MX, right? The chlorides, metal chlorides, when it undergoes hydration, it forms metal ion and halides ion. Right, this is the lattice enthalpy energy, whereas this is the or undergoing hydration. So this is what about the hydroxides and sulfates of group 2, that is solubility of hydroxides increases down the group, whereas solubility of sulfates decreases down the group. Next, we have the anomalous behavior of beryllium of group 2. We are talking about that why these group 2 elements behaves or show anomalous behavior and what are the anomalous behavior. First of all, the reason for the anomalous behavior of beryllium is its small size and high polarizing power. Again, it has relatively high electronegativity and ionization energy as compared to other members. An absence of vacant d orbitals in its valence shell shows the anomalous behavior of beryllium. Now, what are the anomalous behavior? As beryllium is the lightest of all the alkaline earth metals, it has higher melting and boiling points compared to other elements in group 2. Beryllium is small in size with high ionization enthalpy compared to other alkaline earth metals. Beryllium do not form oxides similar to other alkaline earth metals. Next, we are going to talk about uses of S-block compounds. S-block compounds is sodium carbonate, right? These are the carbonate compounds of group 1 elements. Hence, sodium carbonate is used in the manufacturing of glass. Hence, it has importance in the glass industries, softening of water, as well as in paper industries. Sodium hydrogen carbonate, which is your baking powder, as well as soft drink. Again, you can add the usage of sodium carbonate in the soap industries, right? Sodium carbonate into 10H2O is also coming under your washing soda. Next, sodium hydroxides. Sodium hydroxides are also useful in manufacturing of soaps, dyes, papers, and drugs industries. It is useful to make rayons and important chemicals. Magnesium hydroxides acts as milk of magnesia, which is an antacid. Calcium hydroxides to neutralize acids in waste and water treatment. It is used in wastewater treatment, whereas strontium compounds are useful in fireworks, persistent incense, intense red flame. Thank you. Stay safe. Stay tuned.